The universe is currently expanding so rapidly that the distance between distant galaxies grows by thousands of miles each second. But here's what hurts our minds. It is not expanding into anything. There is no cosmic warehouse, outer limit, or larger container waiting to be filled. We are going to embark on a voyage through the most mind-bending concept in all of science. Investigate how space forms itself from nothing. Observe the invisible force. Tear reality apart to learn why asking what the cosmos grows into is like to asking what's north of the North Pole. Please like and subscribe to this amazing adventure. Prepare yourselves. We begin. Imagine a balloon growing in your living room. As you blow air into it, the rubber expands outward, pushing against the surrounding air. The balloon expands because there is enough area for it to do so. Your living room offers that area. This makes complete sense to us. This is how expansion occurs in our daily lives. But the cosmos laughs at this logic. When cosmologists tell you that the cosmos is expanding, your mind automatically envisions a balloon. You see space stretching outward into something, such as a cosmic room or immense emptiness, waiting to be filled. Do you believe there must be a border where our universe finishes and something else begins? This way of thinking feels normal. It feels apparent. This is when physics challenges your comfortable assumptions. The universe is not like that balloon at all. Space grows without pushing into anything. There is no cosmological living room. There's no container. There is no outside. The universe creates the very concept of space as it grows. Consider it like this. Imagine attempting to draw a circle larger than your piece of paper, but instead of receiving a larger piece of paper, the paper itself expands to suit your circle. This seems unthinkable in our environment. Everything grows into something else. Plants grow into the air. Cities grow into the countryside. Ice always spreads across the lake. There is space for the expansion to go. Always. There is a distinction between what is expanding and what it is transforming into. But what if you are both paper and sketching at the same time? Scientists uncovered this mind-bending truth while studying faraway galaxies. Edwin Hubble observed that galaxies farther distant from us are moving faster than nearby ones. At first glance, this appears to indicate that we are at the center of a cosmic explosion, as if we are sitting in the middle. Everything else sails into empty space, but truth is far away. Stranger space itself is expanding. The galaxies are not traveling through space. The distance between them is increasing. Imagine dots on a deflating balloon, but in reverse. As the balloon inflates, the dots spread apart without moving on the surface. The surface itself increases. Each dot notices every other dot moving away. No poisonic. No, is at the center. Now, replace the balloon surface with the 3 dimensions of your living space. The cosmos is not expanding into anything because there is nothing to expand into. It establishes the foundation for future growth. This defies our intuition so profoundly that even bright scientists wrestled with it for decades. Albert Einstein initially dismissed this theory, but this unimaginable expansion is happening right now, quicker than you can think. But how can we be sure that this strange procedure is real? The answer is a lie. Watching light itself be tortured by increasing space. When a faraway galaxy fires a beam of light toward Earth, it travels at a certain wavelength. Blue light, red light, and infrared. Each wavelength has an own signature, much like a cosmic fingerprint. However, as the light travels across expanding space, something astonishing occurs. The space through which the light travels expands along the way. Imagine you're strolling on a moving walkway that is gradually stretching as you go. Your steps remain the same size, but the earth under you grows longer. By the time you reach the end, you've gone considerably further than your feet should have brought you. Light undergoes a similar process, except instead of moving further, its wavelength is stretched. Blue light from a faraway galaxy reaches our telescopes as red light, not because the galaxy has moved away. The light becomes redder as space expands over its billion-year voyage, similar to a racing ambulance changing its siren pitch. Each wave of light is drawn longer as the cosmic fabric expands beneath it. This phenomenon, known as cosmic redshift, demonstrates that space grows independently of the objects within it. Here's the statistic that will rewire your brain. Light from the farthest detectable galaxies has been stretched approximately 40 times its original wavelength. The space through which light traveled has expanded so much that what began as powerful UV radiation now appears as feeble infrared heat. 40 times longer wavelengths indicate that the cosmos expanded by a factor of 40 during the light's voyage. Think about it. The galaxy that delivered you this old light appears small and feeble in our most powerful telescopes. However, when the light initially left the galaxy, the universe was 40 times smaller than it is now. That galaxy was much closer to where our Milky Way would eventually emerge. Space did not just increase a little bit, it expanded massively and relentlessly. But here's what makes it even more mind-bending. This stretching is not happening anywhere else. It is happening everywhere right now. The space in this room is attempting to enlarge the gap between your eyes, while this screen wishes to become larger. The only reason you don't see this expansion is that the electromagnetic forces between atoms are significantly more powerful than the expansion rate. This expansion is only apparent at huge cosmic distances. There are no atomic forces holding the space between galaxies together, thus it can spread freely. Carrying those galaxies about like raisins, raisins do not migrate through the rising bread dough. The dough expands and moves them apart. This is why the question of what the cosmos is expanding into falls apart so thoroughly. You're wondering what the dough is turning into, but you're part of the dough. However, if space stretches endlessly, how far can we see? We live in the ultimate cosmic prison, with walls constructed of time itself. Every night, you go outside and look up at the stars. In that dark sky, you have the impression that you are looking at the entire universe, all of existence, stretched out above you. But here's the truth, which will change how you think. In terms of existence, you see less than 4% of what is actually out there. You're stuck within an invisible sphere. This sphere has a radius of approximately 46 billion light-years. Beyond this border, there is a larger universe, billions of galaxies, trillions of stars. Perhaps other versions of you are reading these words, but you will never see them. Not with any telescope humanity could ever create, nor with any technology that could ever exist. The trap is not composed of walls or barriers. It is made up of the finite speed of light and the finite age of the cosmos. Light needs time to travel. When you look at the sun, it appears just as it did 8 minutes ago. When you gaze at the nearest star system, Alpha Centauri, you see it just as it was 4 years ago. Looking at the Andromeda galaxy takes you back 2.5 million years. The further you look into space, the more deeply you see into history. This is where the trap closes on you. The universe is 13.8 billion years old. This indicates that the oldest light capable of reaching you has traveled for 13.8 billion years. From your perspective, any galaxy more than 13.8 billion light-years away may as well not exist. Its light simply hasn't had enough time to contact you yet. But wait, the trap becomes much more restricting. Remember that space has been growing the entire time. That faraway galaxy was substantially closer to us when it produced the light we see today. By the time its ancient light reaches our telescopes, the galaxy has expanded far beyond 13.8 billion light-years. Today, the galaxy is home to approximately 46 billion stars, light-years away from us. This produces a cosmic prison cell. Everything beyond 46 billion light-years from Earth is in what scientists refer to as the unobservable cosmos. You cannot see it. You cannot detect it. You cannot verify its existence. However, logic and mathematics tell us that it must exist. Consider standing in a deep fog with only 100 yards of visibility in any direction. You can see a circle of ground surrounding you. But you know, the world exists beyond the fog. The observable cosmos is your fog-limited circle. While the true world extends infinitely in all directions, here's a figure that should both frighten and amaze you. If the cosmos is limitless, your observable bubble comprises 0% of what actually exists. 0%. But what is beyond our cosmic prison walls? The most ancient light in the cosmos is screaming at you right now at 600 million miles per hour, carrying a message from the instant reality began. This light has traveled for longer than Earth has existed, longer than our solar system has developed, and longer than our galaxy has taken on its current form. This light first appeared when the universe was barely 300 years old. 80,000,000. The universe was a churning ocean of plasma so hot that atoms couldn't form. This old radiation, known as the cosmic microwave background, can be found everywhere. Switch on an ancient television between channels. This primordial light accounts for approximately 1% of that static. You are practically seeing the afterglow of creation flicker across the screen. This radiation permeates every cubic inch of space. It comes from all directions at once. It's the earliest thing the human eye can sense. But here's what makes this revelation so significant. This light signifies the frontier of what we can see. Until that point, 380,000 years after the Big Bang, the cosmos was opaque. Consider trying to see through the surface of the sun. The early universe was similar everywhere. A heavy fog of plasma obscured all light. No photon could travel more than a few inches. Before interacting with charged particles and being absorbed, something extraordinary occurred. The expanding universe cooled enough to allow protons and electrons to unite form the first hydrogen atoms. Suddenly, the cosmic fog lifted. The universe became transparent. Light might finally move freely through space. The first photons to escape this cosmic clearing are the ones you see today as the microwave background, which is known as recombination. Created the ultimate horizon. You can never look past it. Any events that occurred over the first 380,000 years are forever hidden. It's like attempting to see through a brick wall that encircles the entire early world. The cosmic microwave background is that, and it denotes the utmost limit of observation. Here's the mind-bending portion. This horizon shifts with each passing second of light that has traveled over 13.8 billion years. Plus 1 second reaches us. The observable universe expands by 1 light second per second. That's roughly 100. Every day, 86,000 miles of fresh space come into view. We can see approximately 16 billion miles further into the universe. But expansion complicates this growth as our viewable horizon extends. The real distance to the source of that old light is rising due to cosmic expansion. The galaxy that produced a photon 13 billion years ago is today located approximately 30 billion light-years away. Away from us. We can see where it was, but not where it is now. This produces an unusual circumstance. We are continuously seeing new areas of space, yet the sources of that light are always moving away from us. It's like watching a movie in which someone walks away from you as the screen grows larger. The cosmic microwave background depicts the cosmos when it was smoother than a flawlessly polished mirror, with temperature differences of only a few millionths of a degree. Those minuscule temperature variations would eventually include everything. But what happens when we go beyond this old horizon? Beyond the border of whatever you can see, there's more of exactly what you can see. This may sound uninteresting, but it is perhaps the most disturbing option in cosmology. If you could teleport 47 billion light-years beyond your observable boundary, you'd find yourself in a region that appears very similar to this one, with additional galaxies, stars, planets, and potentially more life. On a broad scale, the universe appears to be homogeneous. Homogeneous means uniform, as in a carefully mixed cake batter in which every spoonful includes the same ingredients in the same quantities. Our investigations of the cosmic microwave background indicate that the cosmos possesses this feature. The small temperature differences we see are smooth and constant over the entire sky. This smoothness reveals something deep about what lies beyond our vision. If the observable universe comprises approximately 2 trillion galaxies, there is an area of equal size just beyond our horizon. It should also include approximately 2 trillion galaxies, with another 2 trillion in a region beyond. The pattern continues indefinitely, or at least well beyond our comprehension. But this is where things get psychologically troubling. If space is genuinely limitless and homogeneous, then every potential arrangement of matter within a given volume must occur someplace. This is not magical thinking, it's mathematically necessary. With infinite space and limited ways to arrange a finite number of particles, repetition is unavoidable. Imagine you have a deck of cards that you shuffle infinitely many times. Eventually, you must repeat the same layout twice. The universe operates similarly, but with atoms rather than cards. This means that other versions of you are reading these words right now, not symbolically, but actually in regions of space so far away that their light can never reach us. Quantum mechanics has ordered matter in every possible configuration, including your current one. There are versions of you who chose not to read this phrase, versions who were never born, and versions in which Earth's history unfolded differently. According to the calculations, these copies exist at distances of around 10 to the power of 10 to the power of 115 meters away. That's a huge amount. If you wrote it out, the numerals would span more space than exists in our observable cosmos. Even if space is boundless, these distances remain finite. Somewhere out there, another you is reaching the same discovery about another, far further away. But wait, this presupposes the cosmos beyond our horizon is similar to the universe within it. What if it doesn't? Recent observations suggest that our local area may be unusual. We appear to be in a cosmic emptiness, an area with lower than average galaxy density. If this is correct, journeying beyond our observable horizon may show denser regions of space with more galaxies. More black holes indicate more activity, or they may disclose sections that are nearly empty. Some theoretical models propose that cosmic inflation, the fast expansion of the universe's first fraction of a second, might have resulted in regions with dramatically different features, physical constants, particle types, and completely distinct laws of physics. These micro-universes might exist just beyond what we can see, operating under laws that would render our physics textbooks obsolete. However, there is a more fundamental question. Underneath all of this supposition, what if the cosmos isn't limitless after all? One of the most beautiful paradoxes in physics is that of an infinite expanding universe. How do you make infinity bigger? Mathematics says this should be impossible. Infinite plus anything equals infinite. Infinity times 2 equals infinity. You can't add to something that already has everything. Nonetheless, our observations plainly reveal that space is expanding everywhere, even though the universe extends indefinitely in all directions. Understanding the true meaning of expansion is the key to finding a solution. When we say the cosmos expands, we do not mean it grows larger in the sense of becoming more infinite. Rather, we imply that the size of space itself increases. Consider it like this. Consider an infinite piece of graph paper with each square 1 inch across. Now imagine stretching that paper. As a result, each square now measures 2 inches in width. The paper remains endless. It still contains an endless number of squares, but the distance between any two marked locations has doubled. This is precisely what happens during cosmic expansion. The universe does not becoming more infinite. The scale factor of space rises, causing all distances to grow correspondingly. When the universe was half its current size, a galaxy that is now 100 million light-years away was just 50 million light-years away. However, this has a frightening conclusion if the cosmos is limitless. Now, it was also unlimited at the time of the Big Bang. This suggests that the Big Bang did not result in an explosion of matter and energy from a single place into space. It was the simultaneous expansion of unlimited space and infinite energy in every area. Wrap your head around this. The Big Bang occurred everywhere at once, across infinite space. There was no center. There is no boundary or outside only boundless space that is abruptly expanding and cooling. Every point in the cosmos can claim to be the center of expansion since it seems the same from every angle. This limitless perspective resolves numerous cosmological mysteries while introducing new ones. It explains why the universe appears the same from all directions. Every location in an infinite homogeneous space appears to be equivalent from our perspective. It also explains why we don't see any edges or centers. There is no boundary or center to see, yet it poses a frightening question. If the universe has unlimited matter and energy, how can we avoid infinite density? The solution is to understand that density is the ratio of matter to volume. Even if matter and volume are infinite, their ratio may be finite. The universe has the potential to contain endless amounts of material, spread throughout infinite space, while retaining an average density of approximately 5 hydrogen atoms per cubic meter. This is where the paradox gets personal. In an infinite universe, every potential event, including your repetitions, will occur infinitely many times. We mentioned this earlier. Every possible version of every imaginable story, every tragedy, takes place somewhere in the great expanse. Every accomplishment, every beautiful moment, and every evil act. If this bothers you, consider the alternatives. A finite world presents similarly unsettling problems. What lies beyond its boundaries? How could space have an edge? What happens if you try to go past that edge? Many scientists prefer infinite models despite their conceptual problems. Latest measurements of the cosmic microwave background assume our universe is either infinite or so vast that any curvature is invisible. The simplest interpretation is that space is endless in all directions. This implies that the expansion you see is not producing more space in the same way that adding rooms to a house would. It is extending the limitless fabric that already exists, yet no new space is generated. What really motivates this relentlessness? Stretching the cosmos creates fresh space from pure emptiness at a rate that would make every factory on Earth jealous every second. The volume of viewable space grows by approximately 10 to the power of 78 cubic meters. That is such a big number that counting it one number each second would take longer than the cosmos has lived, multiplied by itself billions of times. All this new space originates from the quantum vacuum. The quantum vacuum is not the empty space you may expect. It's a boiling soup of virtual particles that appear and vanish in fractions of a second. This phenomenon, known as quantum fluctuation, fills all points in space with energy even in the most ideal vacuum. Quantum activity persists. Here's the mind-bending portion. The vacuum energy has gravitational implications. However, unlike matter, which attracts objects together, vacuum energy produces repulsive gravity. It pulls space apart. The more space you have, the more vacuum energy you will receive. The more space expands, the more space is available for fresh vacuum energy. This causes a runaway process known as inflation. During the universe's initial minuscule fraction of a second, this procedure got out of control. Space grew faster than light could move, not because anything traveled faster than light, but because space expanded faster than light could travel through it. Consider trying to walk over a treadmill that accelerates faster than you can run in less than a trillionth of a second, expanding a region smaller than a proton to nearly the size of a basketball. This seems like science fiction, but quantum mechanics requires it. The uncertainty principle states that energy can be borrowed from the vacuum if it is paid back quickly enough. During inflation, the universe borrowed tremendous amounts of energy to expand into new space. The debt was then repaid using the proceeds from the expansion. It's like getting a loan to buy a money printing machine. Then, using the produced money to pay off the debt, the procedure worked so successfully that inflation exceeded the point at which it should have halted after producing enough space to solve certain cosmological concerns. Instead, it kept going, using significantly more room than was required. Our entire observable universe is simply a small portion of a much larger inflated region. Imagine inflating up a balloon to the size of the Earth. Then, examine only one patch the size of a pinhead. In comparison to the region formed by inflation, the pinhead represents our observable universe. But here's what makes this so weird. The process continues to this day. Current expansion is not inflation, but it functions on similar principles. Dark energy, which accounts for approximately 68% of everything, behaves identically to vacuum energy. It fills the space uniformly and produces repelling gravity, which increases growth. As the universe expands, more dark energy emerges to fill the available space. This goes against all of your energy conservation intuitions. Energy cannot yet be generated or destroyed. Expansion appears to produce fresh, dark energy continuously. The solution rests in realizing that gravitational potential energy is negative. As space expands, matter becomes more distributed, diminishing gravitational binding energy. This negative energy counteracts the positive energy of newly formed dark energy. The universe maintains perfect energy balance while expanding into infinite space. This process will last forever, or at least as long as human minds can fathom. Each minute provides new space, dark energy, and rapid expansion. The cosmos expands not because it requires more space, but because it makes its own space. All of this cosmic ingenuity, however, pales in comparison to what occurred in the first fraction of a second. What proof exists to establish that this seemingly implausible narrative truly occurred? Evidence of the most violent catastrophe in cosmic history can be found in the static on ancient television screens. In 1964, 2 radio astronomers at Bell Labs attempted to reduce bothersome background noise from their antenna. No matter what they did, a constant hiss persisted in their records. They cleaned bird droppings from the equipment. They calibrated their instruments. They directed the antenna in various directions. The noise never went away. That cacophony was an echo of creation itself. What Oz and Robert Wilson had unintentionally discovered was the cosmic microwave background. The Big Bang's afterglow, stretched and cooled after 13.8 billion years of expansion. This finding earned them the Nobel Prize and gave the most direct evidence supporting the expanding universe concept. Here's why this radiation is so crucial. It has the signature of cosmic expansion, which was actually engraved in its wavelength when the light first departed the early universe. It was dazzling, visible light with a temperature of approximately 3,000 degrees, but as space expanded, so did the wavelength. What began as intense, visible photons evolved into infrared radiation, followed by microwave radiation, and finally radio waves. Today, this old light has reached us. At only 2.7 degrees above absolute zero, the cosmic microwave background is completely homogeneous to within a few parts. In 100,000, this homogeneity demonstrates that the early universe was extremely smooth. We should see large temperature fluctuations over the sky, as predicted by inflation theory, if inflation's fast expansion does not smooth out abnormalities. Instead, we see almost complete uniformity. However, the few temperature changes that do exist tell an even more astounding story. They illustrate the quantum oscillations that occurred as inflation expanded from subatomic to cosmic scales. These minuscule waves in the early universe eventually formed the seeds that evolved into galaxies and stars and planets. You exist as a result of quantum uncertainty, which has been exacerbated by cosmic expansion. Advanced satellites such as the Cosmic Background, Explorer, and Planck have mapped these temperature fluctuations with remarkable precision. The patterns they display match inflation theory predictions so exactly that cosmologists may measure fundamental universe features using this ancient light, determining that space is geometrically flat to within a measurement error. We can calculate it. Ordinary matter comprises only around 5% of the entire cosmos. We can measure the universe expansion rate and age with astonishing accuracy by observing static. However, the cosmic microwave background shows something even more profound about expansion. The light reveals that the universe we see today was once compacted into a region about the size of a beach ball. Everything visible in the night sky, every galaxy visible to our most powerful telescopes, used to occupy a volume smaller than your arms could hold. This compression was unlike putting materials into a small box. Space itself was constricted. The beach ball did not contain the early universe. The beach ball represented the early universe. There was no outside, no surrounding space, just a compressed region of space-time that was beginning to expand into the universe we live in today. This knowledge raises a disturbing question. If everything of the space we see was previously compressed into such a small amount, what provided the energy to propel such dramatic expansion? The explanation involves a force that makes up more than 2/3 of everything while remaining absolutely unseen. How can you detect anything that is hidden in plain sight? In 1998, two teams of scientists set out to determine how much the universe's expansion was slowing, only to discover that it was speeding faster. This discovery earned the Nobel Prize and changed our understanding of cosmic evolution for decades. Astronomers anticipated that gravity would eventually prevail over expansion. All of the mass in the cosmos should function as a cosmic brake, gradually decreasing expansion until everything stops spreading apart or begins to collapse back together. The supernovae team, which is studying distance, expected to measure this slowing. Type Ia supernova explode with approximately comparable brightness. This makes them ideal cosmic lighthouses, comparing how bright they appear to how light they should be. Astronomers can compute the exact distances to their host galaxies. When they plotted these distances against the redshift data, they discovered something unbelievable. Distant supernova appeared fainter than expected. This indicated that they were further away than the typical expansion model predicted. During the light's voyage to Earth, space expanded beyond what was expected. The only explanation was that the expansion was speeding. Something was pushing space apart with growing force. Scientists refer to this enigmatic force as dark energy, and it dominates everything. Dark energy accounts for approximately 68% of the entire mass energy content of the universe. It outweighs all conventional matter by more than 13 to 1. It outweighs even dark matter, the invisible structure that holds galaxies together, but we don't know what it is. Here's what makes dark energy so strange. It does not clump or dilute. As space increases, normal matter becomes less dense, spread the same amount of matter across twice as much space, and the density is reduced by half. But dark energy has a constant density. Even as space and the universe expand, new dark energy emerges to occupy the extra volume. This suggests that dark energy's overall influence increased over time in the early cosmos. When everything was crushed together, matter and radiation dominated cosmic evolution. Dark energy existed, but its effects were minor in comparison to the gravitational pull of all that concentrated matter. Dark energy is repulsive as matter becomes thinner due to expansion. Influence became increasingly clear. Dark energy emerged as the main force approximately 5 billion years ago. In terms of cosmic evolution, this basically corresponds to when our solar system formed. Prior to then, growth was slowing due to gravitational attraction. Following that, expansion began to accelerate due to dark energy's repulsive force. We live in the age of acceleration. Every day, dark energy gains greater influence, and expansion accelerates slightly more. This acceleration is slight on human timescales, but enormous in cosmic time in the far future. Dark energy will be so dominant that faraway galaxies will accelerate away from us faster than light can travel between them. They will vanish from our observable cosmos permanently. But what precisely is this unseen force that regulates everything? The main candidate is vacuum energy, the quantum fluctuations that pervade every point in space. According to quantum field theory, unoccupied space should hold an immense quantity of energy. When physicists compute the amount of energy the vacuum should have, they reach a result that is 10 to the power of 120 times greater than what we see. This is the worst prediction in the history of physics. Our knowledge of quantum mechanics is profoundly wrong, or some undiscovered mechanism cancels out the majority of the vacuum energy, leaving only enough to drive cosmic acceleration. Alternative ideas indicate that dark energy is a new field that pervades space, similar to the electromagnetic field, but with distinct features. Others suggest adjustments to gravity on a cosmic scale. The truth is that we are equally ignorant about dark energy. Ancient humans were aware of the nature of lightning. However, this unexplained force determines everything about our cosmic future, causing an acceleration that began in earnest during an even more dramatic phase of expansion. What happens when growth accelerates beyond the speed of light during the first trillion trillion per second after the Big Bang? The universe has expanded faster than it has in the previous 13.8 billion years, and this phase known as cosmic inflation stretched space so violently that portions of the cosmos lost communication with one another permanently. Points that were once close enough to transmit light signals between them was abruptly separated by distances that light could not cross. The universe surpassed its own speed limit. Nothing can travel through space faster than light, yet space has no such limit. During inflation, the distance between any 2 points quadrupled every tiny fraction of time. This doubling occurred so quickly that light couldn't keep up with the increasing distance. Imagine 2 ants on a rapidly inflating balloon. Regardless of how swiftly the ants go, they can never walk together. Here's the number that will end your brain inflation. Expand the universe by a factor of at least 10 to the power of 26. That resembles a particle of sand, suddenly expanding beyond the current observable universe. This growth occurred in around 10 to the power of negative 35 seconds. To put this period in context, light travels approximately 1 foot every millisecond. During inflation, the cosmos expanded by more than 20 orders of magnitude in such a short period of time that light could only travel as far as a proton width. The energy fueling this growth originated from the FLN field, a hypothetical quantum field that encompassed all of space. Unlike other quantum fields, which have zero energy states, the inleton field became caught in a high-energy state known as a false vacuum. This produced a temporary version of dark energy, far more powerful than what we see today. While trapped in this illusory vacuum, the inflated field fueled exponential growth. Exponential growth begins slowly, but then accelerates significantly. If you fold a piece of paper in half 42 times, the thickness equals the distance from Earth to the Moon. The universe went through something comparable, but far more intense. Every infinitesimal instant of inflation, space doubled and then doubled again. However, this technique solved numerous important difficulties in cosmology while introducing new ones. It explains why the cosmic microwave background seems homogeneous across the sky. Without inflation's fast expansion to smooth out anomalies, different portions of the observable universe would have drastically different temperatures. Instead, we get astonishing homogeneity inflation. This explains why space appears mathematically flat. Even if the cosmos began with significant curvature, inflation stretched it so enormously that any leftover bend was imperceptible. It's like inflating a basketball until the surface appears flawlessly flat from your little perspective. However, the most fundamental consequence of inflation concerns quantum mechanics, namely quantum fluctuations in the inflating field, was expanded from subatomic to cosmic proportions. These minuscule fluctuations in energy density served as the seeds for the formation of galaxies, stars, and planets. Every structure in the universe may be traced back to quantum uncertainty, which was magnified by inflation. This means that the galaxy you live in, the star that warms your planet, and the atoms in your body are all the result of random quantum events that occurred at the beginning of the universe. You are a descendant of quantum foam, yet inflation presents a troubling potential. If it happened once, it may happen again. The same quantum forces that caused primordial inflation may still exist, waiting for the proper conditions to initiate another bout of exponential expansion. This might occur here. Without notice, a fresh bubble of inflation might form any place in space, extending outward at the speed of light, and it destroys everything in its path within the bubble. New physics would apply. Our atoms would disintegrate. Our natural laws would cease to work. We would never have predicted it, but this scary potential pales in comparison to inflation's most mind-bending implications. What if our universe is but one bubble in an endless sea of expanding realities? While you read these lines, trillions of parallel universes may be expanding into being. Each has unique physical laws, natural constants, and life potential. This is not science fiction. It is the logical conclusion of inflation theory. If inflation occurred once, quantum physics indicates that it should occur repeatedly throughout a broader realm known as the multiverse. Random quantum fluctuations can cause new episodes of inflation anywhere, at any moment. Each episode generates a bubble universe that grows and cools, potentially spawning its own galaxies, stars, and planets. Our cosmos would be but one bubble in an infinite sea of realities. Here's why this idea is so troubling. Each bubble universe may have different physical laws. Gravity's strength could vary. The mass of electrons can vary. The number of dimensions of space may not equal 3. The majority of these universes would be desolate wastelands. In some bubbles, gravity may be so intense that stars collapse into black holes. In others, gravity may be so weak that matter never gathers to create structures. Some universes may have no electromagnetic force, making chemistry impossible. Others may remain in an everlasting state of inflation, never cooling enough for atoms to form. The great majority of bubble universes would be sterile, but in an infinite multiverse, even the most unlikely possibilities can exist. It must happen somewhere, no matter how unlikely our precise mix of physical constants is. Limitless bubbles provide limitless opportunity for those constants to properly align for life. We live in a habitable bubble not because we are unique, but because we can only exist in inhabitable bubbles. This logic, known as the anthropic principle, explains why our universe appears to be perfectly designed for life. We do not live in a cosmos made for us. We live in a peculiar cosmos in which observers like ourselves can evolve to pose such questions. However, the multiverse hypothesis creates serious philosophical issues. If there are infinite universes, every imaginable event must take place someplace. Every decision you don't make is made by another version of yourself in another bubble. Every catastrophe you escaped affects another version of yourself someplace else. Every dream you never realized comes true for another you. In a parallel universe, the multiverse comprises limitless copies of everyone everywhere, experiencing everything. This limitless duplication renders the concept of uniqueness worthless. You aren't unique. If there are limitless versions of you, your choices are meaningless if every potential decision is chosen by some version of yourself. Your reality is not unique if infinite, comparable universes exist alongside it. However, the multiverse is inherently unobservable. Other bubble universes exist beyond our cosmic horizon. Their light cannot reach us. We are unaffected by their gravitational effects. We can never verify their existence or determine their properties. The multiverse notion generates predictions that cannot be tested. Many scientists believe that untestable hypotheses are not scientific, although the mathematics of inflation strongly supports everlasting inflation and bubble nucleation. The quantum field equations that explain our universe's early expansion also predict continuous expansion and bubble formation across the greater multiverse. If we embrace inflation, we have to accept the consequences. Recent observations have begun to test inflation's predictions more rigorously. The cosmic microwave background exhibits tiny patterns that match inflation theory extremely well. These findings boost confidence in inflation while indirectly supporting the multiverse theory. We could be living in the best evidence for infinite other realms, including this mind-bending possibility. Assumes that our universe has only 3 familiar dimensions of space. Recent developments in physics hint that reality could be substantially stranger. What if expansion occurs in directions we cannot see? The universe could be growing in directions that do not exist for you. String theory. Our most ambitious attempt to unify all physics demands a 9-dimensional space. Instead of the 3 you're used to, there are 6 more dimensions of space right now, curled so tightly that even particles can't detect them. These unknown realms could be expanding alongside the conventional ones. Assume you're an ant strolling along a garden hose. You can move forward or backward down the hose, which appears to be a 1-dimensional space, but it actually has 3 dimensions. The circular measurements around the hose are so small that you can't see them. We might be like that ant, conscious of only 3 spatial dimensions, while the other 6 stay curled up beyond our perception. If these extra dimensions exist, they may provide insight into how the cosmos expands. Our familiar 3-dimensional space may be spreading into the higher dimensional realm that surrounds it. Like a balloon surface inflating in 3-dimensional space, Our space may be a three-dimensional membrane that expands into nine-dimensional hyperspace. The brain world model proposes that our entire universe is a membrane floating in higher dimensional space. Except for gravity, everything we can see, every atom and force, could be contained within this. Gravity is substantially weaker than other fundamental forces since it can only escape into the additional dimensions. The expansion we see could be our brain stretching within a broader hyperspace, but here's what makes this possible, truly mind-bending. Other brains may exist parallel to ours in the extra dimensions. These parallel universes may be separated from us by less than a millimeter in directions we cannot see or move. In another scenario, you might be reading these words from a small distance away. In the fourth spatial dimension, these parallel brains may occasionally collide, creating what we refer to as a Big Bang. The cosmic microwave background we see could be the aftermath of our brain colliding with another in hyperspace. This collision would have generated the energy for inflation, causing our universe to expand at its current rate every few trillion years. The brains may smash again, resulting in a fresh Big Bang and restarting cosmic evolution. However, the mathematics of extra dimensions generates even crazier possibilities. Some simulations show that the extra dimensions may be expanding, while the usual three dimensions remain. From our perspective, we would see expansion and interpret it as the growth of our space. In truth, the hidden dimensions may be doing all the expanding. Consider a balloon with a constant surface size and an increasing inner capacity. We live on the surface, therefore we would never notice the interior expansion. Alternative models indicate that some dimensions expand and others contract. The cosmos may be expanding in some directions while contracting in others. Despite the fact that our three-dimensional slice appears to grow, the total volume of space may remain unchanged. These possibilities are still highly speculative because we cannot directly test other dimensions. The Large Hadron Collider, our most powerful particle accelerator, can look for hints of extra dimensions by detecting particles that appear to vanish into hyperspace. Thus far, no such proof has been discovered. Either the extra dimensions do not exist, or they are considerably more tightly curled than theory suggests. Nonetheless, the mathematics of string theory continues to suggest that additional dimensions are required for a comprehensive account of reality. If they exist, they radically alter what cosmic expansion entails. The question is, what does the universe expand into? There might be an easy answer. It extends to dimensions that cannot be seen, detected, or imagined. Even if extra dimensions do not exist, the form of our familiar three-dimensional space may reveal surprises. What if space curves back on itself in ways that render the inquiry meaningless? The universe might be shaped like a donut, with expansion simply increasing the size of the donut. This seems ludicrous until you realize that the form of space defines what growth means. In a flat, limitless cosmos, expansion expands space with no specific destination. However, in a curved, finite cosmos, expansion may merely increase the size of a closed object that loops back on itself. General relativity allows for three different spatial geometries. Space could be as flat as an unending sheet of paper. Parallel lines would remain parallel indefinitely. The angles of a triangle would sum to exactly 180 degrees. This is the geometry most people envision when they think of space. Space might be curved, much like the surface of a sphere. Parallel lines would eventually intersect, and triangle angles would add up to greater than 180 degrees in this closed geometry. You could travel in what appears to be a straight line before returning to your starting position, or the area could be curved like a saddle. Parallel lines would diverge. Triangle angles would sum to less than 180 degrees. This open geometry extends indefinitely, but with negative curvature. Current observations suggest that our universe is either flat or almost flat, with no apparent curvature. However, flat does not always imply infinite. A sheet of paper is flat, but you can roll it into a cylinder, or connect its edges to form a donut shape. The geometry remains flat locally, but the overall topology is finite and closed. Our cosmos could have such a structure. If space wraps around itself, asking what it expands into is useless. A donut growing larger does not expand into anything. It simply becomes a larger donut. The surface area rises, yet no exterior space is filled. This wrapped geometry might produce observable consequences in a donut-shaped cosmos. Light might travel the entire cosmos and then return to its original location. We may see numerous images of the same distant galaxy in different orientations in the sky. The cosmic microwave background may contain repeating patterns where light has circled the cosmos. Multiple times scientists have also searched for these fingerprints, but found none. Our universe is significantly larger than the observable region, hence, it does not wrap around itself. At the scales we can detect, the cosmos could be a donut, but it's so big that light hasn't had time to circle it even once. However, when you factor in space and time, the shape question gets even more difficult. Create a coherent four-dimensional fabric. The universe's shape incorporates not just the three dimensions of space, but also the dimension of time. Expansion does more than merely stretch space. It influences the interaction between space and time across the universe. Time flowed differently in the early cosmos when everything was compressed compared to now. Clocks would have ticked at varying rates. The concept of simultaneity over large distances would have had a different connotation. As space expands, time moves with it. This space-time extension produces effects that appear impossible. Distant galaxies are traveling away from us faster than light. However, they are not traveling across space at all. Space carries things along, stretching both the time and spatial dimensions. From the galaxy's perspective, it remains immobile as we accelerate away at incredible speeds. Because of this relativity of motion, expansion seems to be the same from wherever in the cosmos. Every spectator views themselves as the focus of expansion, while everything else moves away. There is no preferred reference frame. There is no absolute center or edge that can extend into anything else. The universe expands by becoming more of itself rather than evolving into something else. However, this philosophical resolution of the expansion conundrum raises new issues about the nature of time, and if the flow of time is tied to the extension of space in ways that we are only now beginning to grasp. How does the stretching of space affect the dimension known as time? Time is stretching alongside space, changing everything about how the cosmos ages. When Einstein proved that space and time constitute a cohesive fabric known as space-time, he demonstrated that stretching one will impact the other. As cosmic expansion separates space, it also spreads the flow of time across the universe. This is not simply theoretical physics, it is measurable reality. Imagine you're looking through a telescope at a faraway galaxy, which looks to be moving away from you due to expansion. But here's what defies your intuition. Occurrences in that galaxy appear to move slowly in comparison to surrounding occurrences. A supernova explosion that takes 3 weeks to brighten and fade in a nearby galaxy takes much longer to witness from afar. The galaxy is rapidly receding. This time dilation occurs when the light carrying information about those events is stretched during its path. Not only does the wavelength of the light increase, but so do the time intervals between light pulses. The universe literally stretches time in areas of space that are fast expanding relative to us. Time seems to crawl. This statistic depicts the effect of light from galaxies near the frontier of our observable cosmos. Is redshift by a factor of roughly 10? This suggests the galaxies were traveling away at a rate of about 90%. When they emitted light, events in those galaxies appear to unfold 10 times slower than happenings here. This results in a weird situation in which the age of the universe varies according on your location. From our perspective, the universe is 13.8 billion years old. However, if you could see from one of those distant fast receding galaxies, our part of space would appear considerably younger. Time has been stretched by expansion. This temporal stretching discloses a crucial truth about the nature of cosmic evolution. The early universe did not simply have more squeezed space, it had more compressed time. Processes that take billions of years now occurred much faster. The birth of the first stars, galaxies, and black holes occurred in a universe with a different flow of time than we have now. However, expansion impacts more than just the rate at which time passes. It alters the fundamental concept of simultaneity across cosmic distances. In our daily lives, simultaneity appears to be obvious. If two events occur at the same moment, they happen everywhere. However, relativity and cosmic expansion undermine this premise. Events that appear to you at the same time actually occur at different times. According to observers in faraway galaxies, there is no universal. That now applies to the entire cosmos. On cosmic scales, this collapse of simultaneity renders the question of what the cosmos is doing right now meaningless. Different observers define now differently. The current moment is local, not global. As expansion accelerates, the temporal impacts become more pronounced. Dark energy's impact grows stronger with time. Space is being stretched out at an increasing rate. This acceleration also hastens the expansion of time for future civilizations in our galaxy. We'll see much more significant time dilation effects when we look at faraway galaxies. Eventually, expansion will stretch time to the point that distant events appear utterly frozen. However, this increasing expansion presents a grave dilemma regarding the eventual fate of all. What happens when the rate of expansion is so high that it overwhelms all natural forces? The universe is rapidly approaching a condition of extreme cold and emptiness, that no energy-generating process will ever be conceivable anyplace. This unavoidable destination known as heat death depicts the ultimate triumph of cosmic expansion over all other forces in existence. As space expands, matter and energy will be scattered so thin that the universe becomes a dead uniform emptiness at nearly absolute zero temperature. The timing for this cosmic conclusion is nearly incomprehensibly long. In around 100 billion years, the last stars will run out of nuclear fuel and fall into darkness. No new stars will develop because expansion will have stretched matter too thin for gravity to gather new stellar nurseries instead. The universe will enter the degenerate epoch, characterized by frigid, stellar leftovers. But that's only the beginning of the end. After 10 to the power of 34 years, even protons will decay into lighter particles. Your body's atoms, as well as the atoms that create planets and stars, will spontaneously disintegrate, and matter, as we know it, will cease to exist. Only electrons and positrons and photons will fill the widening void. These quantities are beyond human comprehension. If the universe's current history were compressed into a single second, the proton decay era would span more than a billion years. Even this inconceivable amount of time represents only a small portion of the universe's future. After 10 to the power of 100 years, black holes will be the only major generators of energy in the universe. Hawking radiation causes black holes to evaporate and gradually convert their mass into particles, energy, and stellar mass. To entirely evaporate supermassive black holes, it takes longer than the universe's age. The giants lurking in galaxy centers will survive for 10 to the power of 100 years. When the final black hole dissipates, the cosmos will die from complete heat. There are no temperature differences. Will exist wherever. There will be no conceivable chemical reactions. There will be no computations. No life of any kind can endure. The universe will have reached maximum entropy, a condition of perfect equilibrium in which nothing fascinating will ever occur again. Given our current understanding of physics, this outcome appears to be unavoidable. Dark energy drives growth, distributing matter and energy over ever-increasing expanses of space. Unless dark energy changes its behavior, expansion will continue indefinitely, propelling the cosmos toward its cold, empty fate. However, expansion creates a much more urgent threat. In the remote future, as space expands, faraway galaxies will disappear from our observable cosmos. They do not get destroyed, they simply